We're good? All right. Hello, everyone. My name is David Ahern, and my partner for this workshop is Leon Romanovsky, who's not here in person. He is at home on Zoom. Leon, I don't know if you can hear me. Do you want to say hi or anything? Introduce yourself.
Hi, everybody. I'm Leon Romanovsky, RDMA maintainer. I'm trying to help to David to present this interesting talk. I hope you will enjoy it. I'm pretty sure you will enjoy it. So let's start.
All right. So a few days ago, Leon and I met to discuss content, and at the end of it, he asked me a question. What do I hope to get out of this workshop? And I was thinking about it a lot over the past few days, and I thought, why not just put an intro screen up here right up front, address kind of the elephant in the room, so to speak. My goal for this workshop is to normalize discussions of within this community, within the Netdev community, of any relevant networking protocol. If it's got Linux-based APIs and it's used for something interesting, let's be open to talking about it. AI networking is very relevant today. Its demands for high performance, high throughput, low latency make it a topic. It's a heavily researched and investigated topic on how to do things better, right? And so some of that is coming up with new protocols. Let's be willing to talk about it. When all of this got started, Nickel back in the day, single host, it used TCP sockets getting started to do multi-host for trainings and collective communications. And pretty soon it added support for RDMA because of the performance needs. Well, as IB, the InfiniBand physical layer, gives way to Ethernet, RDMA becomes RoCE. And RoCE is nothing more than a UDP tunnel. It's just Ethernet, IP, or IPv6 UDP-based packets. And so given that, we should be open to discussing anything related to RoCE, what's going on with congestion control protocols, or what's going on with research, how are people deploying it, or any extensions to that, including things like UET, which is coming up later today. So anyway, that's my goal for this workshop, to normalize discussions around RDMA. RDMA is not a four-letter word that should not be spoken. RDMA is a four-letter acronym for operations used to move data between nodes. That's it. So, kind of an agenda, quick overview of what we're going to talk about. Let's set a foundation for what we mean by some of the AI networks, and in particular, focusing on the nodes, the end nodes of those AI training networks. Get into just a quick refresher about when you say Netdev. What does it mean? What do you mean by Netdev or a Linux networking stack? And then take a peek at the IB verbs networking stack. IB verbs, again, it's open source APIs. These come in the kernel. It's just an alternative control path for how you do something. Let's move on to why RoCE has become the dominant protocol for AI training. There is a reason, right? And so let's discuss how socket-based networking works. Let's go over the performance of it, some of the extensions that have gone in recently to make things better, and then look at what RoCE can do. And then from there, I want to talk about something I presented at NetDevConf in 2022. It was an architecture that showed how to use Linux TCP with queue pairs. Let's come back to that and introduce how to do message framing over TCP. And also, I want this to be an interactive discussion. So we've got Leon available for answering questions. Myself, let's make this interactive. And so if you have questions, please ask as you go. Let's make this an informative hour. So anyone who's done any reading on AI, it's a lot of papers, a lot of topics, a lot of blog posts. Matterf is, for one of those companies that will happily share notes about how things are going. For example, right now, they have networks that have 24,000 GPUs across 3,000 servers. All their physical ports are running at 400 gigabits per second. They're targeting upwards of 128,000, or at least what they're putting online. They're targeting up to 128,000 GPUs across 16,000 hosts. That is a lot of hosts, a lot of endpoints to get coordinated in a training session. Looking at XAI, Colossus. It depends on how much you believe in the press, but you know they're advertising 100,000 GPUs in a single RDMA fabric, 400 gig ports again. Pushing up to 1 million endpoints, 1 million GPUs in their training network. Again, that is a lot of endpoints to coordinate. AI models themselves, LLMs, it's not uncommon now to see trillion parameter models. And so you're having to push a lot of data for these training sessions. You have to push a lot of trainings to each one of the GPU, a lot of data between each one of the GPUs, for example. And so right now, what's come out of it is a lot of specialized, dedicated Ethernet networks, for example, like the rail design, where you have every NIC has its own GPU that it's sending data to or receiving data from, okay? I don't want to spend too much time talking about the actual spine leaf network side of it, because that also changes a lot based on who's deploying what. And the focus here is going to be on the actual endpoint servers themselves. The ones that are generating the packets or receiving the packets that have to get processed or getting handled. And so when you look at what an individual host has to do, right? We're not talking about a web server where we're trying to support millions of flows. We're talking about servers that have to handle a small number of very large flows. So for example, if every GPU has its own NIC and the NIC is running at 400 gigs, you're trying to have 8 400 gig flows handled on that server. Anyone who's done any high performance network testing on an OS or on a Linux-based server knows every single cycle matters. Every nanosecond matters. You got to be doing something useful with it. And what RDMA has basically said, you have to get the OS out of the way. Every system call, every generic feature, every hook that exists is just overhead. I think at this point, we all understand zero copy is an essential. Right? We've got zero copy everywhere now with the recent work for the DevMem approach, for example, and now Uring extensions. Another part of that gets into, you've set up these servers where every GPU that's on the box has its own dedicated NIC for sending and receiving data. You don't want to have memory copies, which means you need to make sure that this data that's coming in or data that's going out goes straight from the GPU through the NIC out to the network, or in from the network and going straight to the GPU. So it's essential that we are not getting the CPU involved, that we're able to do direct communications. Now, when we start getting into the actual packet side of this, you know, what happens when packets are dropped? What happens when we start getting congestion, right? Some of this is going to be a transport problem or a hardware problem. How does the hardware handle something that's out of order, or how does hardware handle a drop? But at the end of the day, the payloads need to be landed in the correct place in the memory that was posted for that message, and the work completions need to be done in order so that you get message 1 completion before message 2 completion, etc. The next thing is you have to be hardware based. You're not doing all of this in software. No one's running 400 gig software stacks, okay? Ethernet header protocols are simple to create. There's nothing magical about an Ethernet header, an IP header, a UDP header, right? Hardware is very good at mechanical things, okay? So we don't need to get caught up in something that's, you know, considered proprietary when all we're doing is handing off big payloads to hardware, and hardware is creating wire packets out of that. Right? And so if you look at TSO, for example, with the Linux networking stack, you can have a header with a large payload. Hardware will chop that up and create wire packets out of it, updating fields in the TCP header or in the IP header as needed so that you've got legit packets going through the network, right? Again, it's a very mechanical task. And ideally for AI networking, you want to avoid retransmits at practically all cost, right? Drops hopefully aren't happening. If you got dedicated networks for this, out of order conceptually shouldn't happen, but 16,000 nodes means you've got a lot of hops going between them. On a congestion side of this, that ability to say, you've got all these different flows trying to run at hundreds of gigabits per second. If one receiver gets slowed down, the ability to shut down just one sender as opposed to a switch port or an entire server, this is just one of these areas where you have to think about it, and then it's an area for active research on how to handle things like this, okay? So this gets into the actual server itself and what we kind of need hardware-wise, and then how we need to think about what the software is doing. So hopefully this picture isn't new to anyone in this room, anyone who's been around Linux Netdev for a while, right? Hardware, you've got some piece of hardware that does some fancy things for networking. The Netdev is just a virtual model that presents that hardware device to what we think of as the Linux networking stack, right? And that's going to be the one where maybe you don't care what kind of packets are coming in. It's got a whole bunch of RxQs. You've got an RSS that you've installed that says distribute these packets across the RSS set so that one CPU isn't dominating packets. The driver will create SKBs, send those up the stack. You've got a page pool that you're trying to be more efficient in how you're pushing buffers out there. So this is all kind of the anonymous networking style. You don't know what's coming in necessarily, or maybe you do and you've created a specific flow and all of this TCP traffic for some precise end tuple is coming in on a particular one, right? But nonetheless, you're letting some kind of generic infrastructure handle how the packet goes from hardware up to the application and down, right? The Linux networking stack also contains things like the TCP implementation, UDP packet handling, network addresses and routing. How do you know whether that endpoint's reachable, for example? You got to resolve where the next hop's going to be. So you got this neighbor cache that keeps track of, the destination address is X, but its link layer is this, or its next hop for the link layer is this. So this is all kind of part of the generic Linux networking stack and typically accessed through socket APIs. And those socket APIs tend to be done through a library, in this case, libc. So now let's look at the IB side of the world, right? And again, these are just software APIs. They're in the Linux kernel. They're open, they're available. The RDMA core, in this case, provides your library. You'll have an RDMA CM for the connection management side of things if you need help getting set up with your peer, getting that initial QP set up. You've got libiv verbs, which has a consistent interface for applications to use the verbs API to set up that control path. And then you've got that provider, which is the vendor unique sides of things, right? So the hardware, the IB driver, and the provider should all be thought of as one kind of, one vendor-based entity and how it coordinates things that are a privileged side, which is the driver, and things which are the user space side and helping it work with a consistent interface to an application. So you use these verbs APIs, for example, to create queues with hardware. So in this case, you're going to let user space submit things straight to hardware. You'll have a receive queue, which you can use to post buffers or get notification completed work entries. You can have a send queue where you're trying to send work down to the NIC, have it take the buffers and create the wire packets. And then there's completion queues for getting notified when the work is done. Okay, so this is kind of just a general overview, quick picture of a verbs architecture. So RDMA data path. It's typically message-based. I think it's always message-based. And so what that means is you push down a work request, and the work request will say, here's how many bytes, maybe in a scatter-gather list, that you're sending through this QP to someone else. You're sending it through opcodes. Those opcodes can be like a send request, or an RDMA write, or an RDMA read. If you're having to send multiple packets to complete that request, you'll use a first, middle, 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 last kind of syntax where you're basically saying, here's the first packet in this message, here's the middle packets in this message, and then oh, here's the last one. So now the endpoint knows this message is all done, and it can send the completion up to the receive side of it. RDMA write, so I guess to finish up the send side of this discussion, this is probably the closest thing to what Netdev people would relate to, in the sense that the RX side is expected to post buffers for this message that's incoming. The send side is posting a message, goes through a stack down into hardware, and the wire packets are created, right? And so when I do some comparisons later, really it's the send operation that we're doing the comparisons with. RDMA write, on the other hand, the receiving application said, hey, you can write X amount of data to this specific address. So now I don't have to post anything, it's just gonna write straight to my memory. And then RDMA read is kind of the inverse of that, where the peer has said, hey, you can read so many bytes from this particular memory region and this particular address. And then the local end will post the buffers and then send their request to pull from that other side. All right, so before we go to the side-by-side, Leon, did I miss anything in that description?
I don't think so.
Okay.
Was totally right.
Okay. Leon is the expert on this. I am still up and coming. Okay, so moving on, the IB stack and NetDev, right? So we mentioned that RoCE is basically UDP tunneling, right? So the IB stack has leveraged quite a few things from the NetDev side of the world, so that you don't have to reproduce all this in just the IB world to get the same functionality. So for example, the hardware will have a front panel port. Software is going to want to know, is the carrier on? What speed is this device running at? What was the MTU that this particular network port is using for packets? Okay, so that information is going to be shared where the IB device that's been popped up to represent the device to the IB side of the world, it will also handle the NetDev notifiers, so it gets told about what we think of as the NetDev side of the world. When you look at L3 addresses, anytime you put a network address onto a NetDev, the NetDev notifiers, again, the IB stack says, oh, let me just add this network address to my GID cache, okay? When some RoCE application is pushing down an address handle that says, you know, I'm gonna send it to this peer, the core IB verbs code will look up through the routing tables inside the Linux world, the NetDev side of the world, and say, hey, is this endpoint reachable through this port? And if so, give me the neighbor entry that goes with it so I can get the next hop. So again, it's just kind of that essential information you need to create the headers that you send out on the wire packets. And then of course there's things like the connection manager, which again go through just normal sockets. So really what I'm trying to get at here is you have a single piece of hardware and it has virtual devices, be that a net device or an IB device, and that's just a representation of that device to a software stack, right? And again, these are open source APIs inside the kernel, just two different ways to configure things. Oh, and finally, see, I don't do a lot of this. This was something that Leon had just put in recently. Another side of this gets into the data offloads. And so the NetDev ops, for example, someone's already figured out how to tell hardware through the NetDev operations how to do an IPsec or a MACsec offload. So RoCE traffic, just UDP tunnels. So if it's going to do something over an IPsec or a MACsec, you can just use those NetDev operations just like anything else for configuring the hardware, right? So again, it's a synergistic play between the two software stacks. All right, so RoCE, standardized protocol, right? There's nothing proprietary about this. Two endpoints are supposed to work regardless of vendors. What you're really talking about are just UDP packets, right? RDMA over Ethernet is just UDP encapsulated packets. You're sending to a well-known destination port. The source port, kind of like VXLAN, is just going to be some entropy to help you figure out, different paths through the network. QP, so the Q pair number shows up in an extension header And that can be used to do your precise flow steering in hardware, okay? Again, the basic RDMA ops, you've got that send that's going to happen to send data from one side to another. In this case, all you need there is the BTH header. So Ethernet header, L3 header, UDP header, this base transport header, which has things like your opcode and your queue pair number. Who's receiving this? So RoCE tends to work in a requester responder model or a requester completer model where one side's requesting something and the other side's going, oh, let me respond to this. Here's your RDMA read request, for example. Or the requester completer model where somebody, one side is being requested to send something over and then you get notifications when it's complete. And again, it's message semantics. The work request come down, whatever blob it's in that work request is considered a message, and then it gets sent over in a series of packets through that first, middle, last kind of series. And really the soft load is just, it's almost identical to the TSO concept where you're pushing down a large payload and hardware is mechanically deriving headers for it to send out. There is an expectation with RoCE, everything always arrives in order. And if something arrives out of order, you drop and you ask for retransmit from that PSN. So networking performance. I mean, at the end of the day, if you're trying to train some model, what really matters to you is how fast each round can get done. Because if you're doing a number of rounds to converge a model, you need that model to complete as fast as possible. You got these expensive GPUs, expensive 400 gig ports, expensive servers trying to run all of this. You want to get some return on your investment for that. Well, if you look at ConnectX-7, for example, these are 400 gig ports. And as I mentioned earlier, most of these deployments you see online, they're advertising that they run with 400 gig ports. Well, that gives us an easy side-by-side comparison of how RoCE can compare, how RoCE's speed and performance compares to socket-based networking. So again, if you look back at the talk I gave at LPC in 2022, I got into what kind of settings are needed, how fast can you make Linux TCP work. I had to pull those slides out to do that again here, to do all these little magic configurations to a server. Some of them aren't necessarily realistic for what you'd actually want to deploy. It's more getting an apples-to-apple comparison to RoCE to the greatest extent possible. So for example, turning off QDisk, no QDisk at all. Well, RoCE's going user space to hardware, so RoCE's not using a QDisk, so that seems fair. Same with net filter rules. We know if someone installed Docker on a server, your performance just went down a little bit. You can't run TCP dump, for example. So you got to make sure there's no packet socket apps are up and running, LLDPD or TCP dump or any of those kind of things. We pen the flows to make sure that the TCP, it's running on a similar cache, L3 cache, as the soft IRQ handler that's dealing with the packets coming in. We enable all the hardware offloads that the ConnectX-7 has, from GRO, TSO, GRO list, made the ring size bigger to make sure we're not dropping anything in the NIC. We enabled TCP, and I would say Big TCP is one example of where we weren't quite apples to apples because the Big TCP is capped at 512. Well, another slide I'll show you that the RoCE is using 2 meg message sizes. So to have Big TCP go up to 2 meg, or you drop 2 meg down for its payload size to create the wire packets, might be a little more of an apples to apples comparison. But in this case, I didn't have to make any changes to the kernel. And then of course the big one is you got to have zero copy. And so I did not add devmem zero copy or IOU ring zero copy to iPerf3. Instead, I went with the message trunk that I was using back in 2022. And the reason is this is zero overhead RX zero copy. You're not doing any copy between kernel and user space. And you're also not incurring the overhead of any operations to return memory to a pool. Okay? So it's really the best you're going to get from an RX zero copy. You're just assuming that the payloads landed where they're supposed to be. And I guess finally, the last one there is the 9,000 MTU to get the largest packet sizes out and the fewest software packets going down the stack. So with all of those server configurations set up, the best I could do with a TCP flow was 215 to 220 gigabits per second. Okay, it's receive side limited because that soft IRQ on the receive side was at 100%. TX side looked like you could do a little more. I did not get into optimizing the Mellanox driver to reduce some of this overhead. I'm sure some of the Mellanox developers on here could look at some of this and go, we've already solved that problem. But given where the limits are and given the top speed, I don't see how, even making some modifications to driver here, for packets to walk from user space, all the different layers, all the socket calls, the QDisk, the net filter rules, the eBPF hooks, all these different layers and generic infrastructure that a general purpose OS has, all of that adds up. So I don't see how we're going to get to 400 gig walking that entire stack. Then we go to RoCEv. Same hardware, same exact server. Literally did nothing. Control C on the iPerf3, start up IB-SAN bandwidth. Now, one thing about RoCEv is that it doesn't use exactly the same MTU as on the port. It uses the power 2 under. And the max that it has for an MTU is 4096. So in this case, RoCEv's payloads were 4096, and then the headers were on top. Just off the bat, no configuration needed, 392. So where socket networking, we need to have 2 TCP flows to hit line rate. With RoCEv, we're practically there just by default, right? And so that's a very important lesson. If someone is trying to use Linux networking for AI training, you have to understand where that overhead is and get the overhead out of the way. I mean, that's kind of the fundamental problem, right? And this is not meant to be a knock on the Linux networking stack at all. Like, I've spent a lot of years working on that. It's just really meant to be a realistic statement about where things are. Doesn't mean it has to be, the status of things going forward, right? And I have a proposal later where I get into how to use Linux TCP with QPs, which I think we're gonna go way beyond the 400, okay? But when you look at what RDMA and RoCEv are doing, this control path going through software APIs and then the data path going straight from user space to hardware, that's kind of the ideal thing you have to do because you have gotten all of the overhead out of the way. You're letting your control path, any management policies you want, is this connection allowed, for example, do that in the control path. You don't need to analyze every single packet to say, is this one allowed to happen or not? In addition, you don't have any system calls that you're having to do with RoCEv. You just insert something into the queue, hit a doorbell. In some cases, you hit a doorbell. Maybe you don't have to hit a doorbell. It depends on how the hardware is set up, looking for work to be done. But typically, you'll hit a doorbell, but you can do some batching on that to amortize the cost of the PCI transaction to go down. You've got memory regions instead of memory buffers, instead of anonymous pages or buffers that are being posted. So instead of having to keep track like this page pool design that we've got for Linux, it still adds overhead. So it's better than going out to the memory system cache, the system memory cache. You're able to reuse some DMA mappings, for example. You're able to have things being on a per CPU lock, but it's still some cycles that are being spent managing where to land payloads. Where with the RDMA concept of, here's some memory I own. I told you about this memory. You've mapped it. You understand the translations to it. So now you can write directly to it. And we don't have to play this game about, well, here's another page, here's another page, here's another page for a packet. You've got plenty of memory for whatever I'm expecting to come in. Another one is that you're not having to build these SKBs per packet. No matter how light you make them, no matter how many NAPI caches you have, it's still overhead just to allocate an SKB and then to fill in some metadata. I think that's about all I was trying to make around this, the Rockies RDMA data path. All right, any questions so far? Everyone just waiting for me to stop talking about RDMA? Okay, so I'm sure people who are paying attention to recent developments have noticed the DevMem patch that Tamina and Google was working on for quite a while. I do like the fact that we finally have a zero copy solution available for Linux networking. That's long past needed. Even if it isn't used for AI training, for example, I still think it's a big win for the Linux TCP stack. So when you look at how that works and you avoid the zero copy, but you still have this page pool that exists, right? So user space had to take a DMA buff and it has to tell the generic networking stack about this DMA buff. And then you've taken that DMA buff and you've separated that into a bunch of page pool entries because you're having to supply hardware with some buffers to land packets as they're coming in. But what you've also got is these set socket calls that are needed to return memory back to that page pool, okay? You've also, when these packets land in GPU memory, that's great, no zero copy, but it's still an anonymous buffer style. So for the thread running on the GPU to make use of it, you have to linearize those individual buffers into something continuous that the thread's expecting, and also so you can return those pages back to the pool for the next set of packets that are coming in, right? Again, it just gets into overhead that's going to limit your ultimate throughput that you're going to get through this kind of a solution. I also don't want to ruin Jamal's talk later because I know he and his team have done some extensive work adding support and looking at the TCP DevMem and the IOU ring solutions. So while I wanted to get to that and add support to iPerf3, for example, I did not have the time to do that. So no spoiler alerts for Jamal later. Okay, so IOU ring is another one that's had some work recently. Pavel's here today. Him and David have done a lot of good work on avoiding one of those, again, critical overhead paths, which is system calls. So the IOU ring extension lets you avoid system calls to return memory back and also then to receive references for where packets were landed, right? So again, some needed improvements to a typical socket-based networking style, but there's still going to be enough overhead in it that I don't see how just avoiding system calls is going to push you from the upper hundreds, maybe low 200s, up to the 400 gig range. But happy to be proven wrong if that team gets a hold of some hardware and can do those kind of experiments. The 116 gig, that number comes from, I think David had that number in his cover letter when they did the IOU ring, the ones that got merged. And so the GPU side of that is not supported now, but my understanding is that's coming, and then it shouldn't be that big of a deal to get that extension added. But again, the fact that it's host memory and having that RX zero copy is a much needed feature for Linux. So now coming back to 2022, and how do you bring in Linux TCP with QPs? And I want to say again, this is not iWarp. Please do not confuse this with iWarp. What we have done is essentially taken the two software stacks and brought them together in a way that we avoid system calls, we avoid walking the full stack, we avoid having to deal with receive queues where we're constantly having to supply buffers to it, okay? What we've done is we've set up a socket with a peer, we've set up a QP with that peer, and as soon as the socket's established and we know who we're communicating to, we've got that 5 tuple that we can program into hardware, we let the data path be driven strictly by QPs. And so what you'll notice here is that means we have some software in the loop. We're not just doing software queues down to hardware. We're doing software queues to a driver that can leverage the Linux TCP engine, its congestion control, and the features that it's got in it and all the work that's going into making it faster and faster. And so then the IB driver will manage those queues for that particular flow, and it does the conversion between a work request was posted, run it through TCP, TCP decides it's ready to send some packets, we throw it into the TX queue, and out they go. And then on the receive side, same thing. We can see these packets are landing, let TCP know about it. It can handle things like the SACs for anything that's missing. And then we've got the entire message, send a notification up to the application of, hey, your message is here. So one thing that's needed to make this work is message framing. Like I said, RoCE and RDMA, they work over messages. So we need a way to take a byte stream and tell it when a message one starts and when it ends. And then if we're doing these first, middle, last kind of opcodes, we need a way to tell, hey, the receiving side, this is a big message, and this is only one part of the message. We also need to be able to handle things like an immediate data, so 4 bytes of immediate data and the ICRC, which is expected in the RDMA side of things. And then we want the packet to be self-describing. So for example, when you look at the RoCE packets where you get a first, middle, last kind of a scenario, the peer has no idea how many middle packets there are. It was never, not necessarily told ahead of time that I'm going to send you exactly this number of bytes. And so what we wanted was the packets to be self-describing so that the hardware on the receiving side knew exactly where a given packet goes within the either the buffers that were posted from user space or if it's an RDMA write, which we're getting to, where exactly in memory it goes, okay? Now, one thing we have to deal with is TCP options, right? We don't want to modify the byte stream because injecting data in the middle of a byte stream has all kinds of problems. So what we can do is use a TCP option. TCP options are limited to 40 bytes. Well, that's the theoretical limit. Timestamps are kind of important for pause, right? You want to know when you're wrapping over that sequence number because if you're sending 40 gigabytes of data, you're going to be wrapping that sequence number over pretty quick. The timestamps take out 8 bytes. Well, TCP option in its TLV style, you lose another 4 bytes. So what you're really talking about is 28 bytes of data. How can you leverage that 28 bytes of data to handle the things that an RDMA world expects, like an opcode, as well as the things that make TCP work well, like the timestamps? And so this is a BTH TCP option extension that we've been using and do want to have standardized if possible, or at least start that process. And so we've got the flags in here that say, yes, we assume a timestamp is present, and so we can have a flag that says it. We've got some inline RTR ready to receive, and the peer acting, yeah, I'm ready to receive, or I've received your ready to receive. And then we got the RDMA opcode so that you can tell the hardware what kind of operation is happening. We'll have the message number and then the message byte offset. So for any given packet, where inside of this message does this payload belong? And then of course the CRC and timestamps and the immediate data right after that. So this is something we've been playing around with for coming up on 3 years and hoping to get standardized. Final thoughts. Like I said, I really want to see the Netdev side of the world. And I know for anyone here who works on drivers, you're like, what's the problem, right? Because if you're working on a driver for a company that does both RDMA and Linux networking, of course, you deal with both on a daily basis. I understand there's some friction that goes way back. I'm not a historian. I wasn't around during those days, or at least not paying attention during those days. But we have to be able to talk about the RDMA side of the world and how to better leverage some of the RDMA, the verbs APIs, to get more out of just networking in general. And I'd like to see this conference open to more talks around anything related to these transports. There's the UET talk later today, introducing UET to the community. And just remember that RoCE, for example, is just UDP, just a UDP tunneling protocol, right? I think that's, yeah, in future conferences, I'd like to see a continuing workshop. I'd like to see this happen every time. I think AI networking is just such a hot topic. There are so many issues to be dealt with that I would love to have this be a recurring workshop where we talk about what's going on, what we're thinking about, what our problems are, things we want other people to know. Okay, and with that, I am done. The slides will have some references to the Meta and XAI platforms if anyone's interested in seeing those. But if you just Google a few things, more reading material than you can possibly handle. All right, any questions?
So my understanding of RoCE is that it is a container protocol, where that RoCE is a container protocol, where there is a standardization on how the protocol works, but the messages sent between is still very vendor specific. So you can't directly connect like NVIDIA to AMD and have RDMA just work because it's not going to understand the messages. So do we need to start coming up with a standard on how these messages are sent so we can have cross-vendor RoCE support?
So
Leon, did you hear that?
Yes, I heard it. I don't know why did you, I have no idea why did you say, but there is a yearly interoperability, not conference, but workshop in some of the University of Hampshire, which actually takes different cards from different vendors and put them on one server on one network and runs interoperability tests. So to get RoCE V2 certified or InfiniBand or whatever fabric you want, you need to pass this interoperability test. We also have a software model RoCE, which is called RoCE, so soft RoCE, which implements RoCE interface and RoCE protocol completely in software. And this software interface actually works pretty well against NVIDIA or Intel devices. So we can connect one side software, RoCE emulation, another side real hardware, and that will work.
Oh, okay, thank you.
Yeah, that's basically was my response, but I wanted to defer to the expert, which is I know there's a soft RoCE driver, and you can check compatibility with that implementation and ConnectX, and I'm fairly certain we've done those tests internally, and they were compatible. So, yeah, I wonder how much of that just gets into the FUD that gets out when someone doesn't like a protocol or wants to downplay it. They throw out the, oh, is it compatible kind of questions. But RoCE V2 is standardized.
I have a simple question regarding this TCP QP story. I understand that the application is still talking to sockets, or is it talking to queue pairs?
No, for the solution that we've created, when you kick the data path over to the RDMA style, it's submitting work requests just like it would for any other RDMA app. So you can do a post-send, post-receive call through the libIB verbs.
So you are extending basically the RDMA subsystem to have a special QP type, which is special something?
So we made 0 patches to Linux TCP to interact with it. Yeah, and we made no changes to libIB verbs. So we just pass the socket down to the driver once the connection's been established and both sides are ready to start transmitting data. And so the driver takes over the socket.
But the application still talks to the socket.
It does not have any knowledge of the socket. It never even knew the socket existed.
Okay, interesting. I didn't get it, but Sounds good.
Yeah, that was one of the key points, is that you're just another RDMA application, so to speak, and you've created a Q-pair through libiv verbs, through those APIs. And behind the scenes, you've said, oh, well, we want the transport to be TCP. We want this congestion control protocols. We want the retransmit capabilities. And so we will cause it to use TCP instead of RoCE, for example. So a selectable protocol.
Actually, kind of connected question, maybe.
Yeah, just speak up a little bit.
Yeah. Can you hear me?
Yeah.
Yeah. Hello, hello. What is the overlap with the connection manager here? Because it is doing something similar, right? Where you have the connection created somewhere else, and then you pass it down to the
Yes.
RDMA side.
Yes. Yeah, we have a connection manager implementation. So if you're using the TCP and you use it with the CM notation, then the socket gets created by the connection manager and gets handed off to, so it's our version of a connection manager and then handed off to our version of the IB driver.
Okay.
Right, so
I
the
need to
RDMA
think about it.
CM, it's just implementing the accept, connect, typical function calls, and then handling the transfer of it.
Okay.
There's nothing magical about that, but you can also do it in a non-CM way where our provider can do the connection for you, or something else can do the connection and hand it off to, right? A socket's a transferable file descriptor, and so there's lots of options on how to get it created and established and then hand it off to us.
Okay. Thank you.
David, it's worth to add that we have RDMA CM, and RDMA CM it's actually pretty basic and pretty mostly usable for kernel verbs users like NVMe over Fabric or other storage protocols. In outside world user space, where some users who are still using libRDMA CM, but many of other users actually implementing CM by themselves. So what did you do for your own Linux QP, Linux TCP QP thing? It's pretty standard in our RDMA world. You can do whatever CM management and CM logic you want. You are not limited. We don't limit you.
Okay, that actually makes sense. Like, I worked with this a while ago, and there was always the problem of creating a lot of connections, and you wanted actually the connection manager out of the way. And if you can have this in, like, from the application, yeah, that's quite useful. Okay,
Yeah,
that makes sense.
there's lots of ways to create the TCP socket, and then, like I said, we just hand it off to our module to turn the data path into QP-based.
Yeah, thank you.
Yeah.
So I was around back in the day when we did have this discussion about the infamous TCP port space patch, mostly in the context of iWarp. But what is the feeling here with this approach of the TCP with Q pairs and handing off the socket? Because it feels awfully the same. It's just maybe going through a different path of effectively consuming a socket in the TCP land that RDMA takes over. And I mean, this is like 15 years ago when it was very controversial. So I'm very curious to see where we're at.
I'll defer to Srijit on that.
I'll say a few words and then I'll point at Bernard and he'll say the rest. But so Bernard, if you can't see him, is
The iWarp maintainer.
yeah. So yeah, future questions can be directed that way. But the high order bit here is iWarp tried to do effectively the DDP layer on top of the fundamental IB infrastructure, right? So it actually required you to do 3 layers of translation to get to the endpoint, and it tried to do a tow, which is a completely offloaded TCP engine. What we are doing here is actually sort of an onloaded TCP engine, but more importantly, it's going in the reverse direction. You're actually doing message framing on top of a TCP stream rather than converting messages into a TCP stream and trying to find coherency that way. So the functional model here is much simpler. The lookup is simpler, but it does require hardware to operate in a certain way for it to work. I don't know if that helped at all. Okay. I think I saw a hand somewhere up there.
For those at home, that was a thumbs up by PJ.
No, somebody else had a question?
Hi. I have a bit of tangential question. I see this combination a lot, but you didn't really cover it. I often see RoCE mentioned combination with IPsec. And my main question is, when you want IPsec, for example, who makes the request? Like, is it a client which says, I want extra things on the RoCE to be encapsulated, or is it a system which decides that?
That's definitely a Leon question.
Yeah, when you're creating a connection of to talk about from one host to another, you're actually doing it through IPsec. You need to say what is policy, what does it say, so what is IP from one side and what is IP from another side. So once you created this connection, under the hood, all messages which flew through this connection will be encrypted, including RDMA. RoCE is byproduct of this connection. Nothing more. I hope I answered your question. So just to summarize, the one who created connection will the one who will say if this connection is going to be encrypted or not.
So if I can follow it up, like if you say, let's say IPerf, when you start IPerf, do you use IPerf to tell this should be IPsec, or is the system already decide for you this is going to be an IPsec?
No, it's not IPerf. It's definitely you as a user needs to say, I want from host A to host B to encrypted connection. There is no difference. Again, there is no difference between, at least for IPsec, between regular TCP flows and RDMA flows. So in IPerf for TCP, you before created a policy and SA and connected and your connected VPN. Exactly the same goes for RDMA. You need to create this connection before. You need to set this connection is going to be encrypted, and later run your traffic as is without any.
Thank you. So the last question is like the number you showed, 392 gigabits, is it with IPsec enabled or is it without?
I did not run any tests with IPsec, no.
I can assure what we at least 6, 7 is capable to run 400 gigabit IPsec flow. So we can do it in encryption.
I have another question. If we have a QPR now, and we have all this nice semantics like writes and reads and atomics, currently you are supporting just send receive, right? Currently you are supporting just the send receive model on your QPRs. And wouldn't it be nice if there would be a way to also at least support RDMA write operations? And how would that be possible with these few bytes in your pseudo header and without memory reservation at the peer side?
So you're saying using RDMA write with TCP?
You are doing RDMA write?
We're doing send only right now.
Yeah. Is there a way to support RDMA write in your model?
How do you want to answer that, Srijit? Yeah, so I think it's something we would have to investigate, how to handle a TCP write, I mean, a RDMA write with TCP.
Yeah, I think one of the things, actually, I had to step out, so I don't know if you covered that. This header is a TCP option right now, right? So we would need an REth header, and it would have problems being a TCP option. So there's some practical issues with it. I don't think it's architectural. It's just. I'll just come stand next to you.
I have to ask a question. You could maybe do things like doing RDMA write from a variable offset, so that you have a file descriptor and you are writing at an offset, a memory mapped region or something, right? That would be possible, maybe. That would be interesting. I mean, yeah. Okay, sounds interesting. Thank you.
So how much of the RoCE performance, how much of that, because I believe the stack is in the hardware, correct? All the way to UDP. You have the parsing done in hardware, you have multiplexing.
When you say the stacks in hardware, what do you mean by the stack?
You have UDP in hardware for it.
What does it take
multiplexing, yeah.
What does it take to create a UDP header?
I mean, but all that parsing is done in hardware. The stack doesn't do any of it.
Well, no, but my meta point is Ethernet headers are pretty simple. There's not really any state there, right? You're just saying who's your next hop. IP headers, pretty stable, it's simple. UDP header is extremely simple. Source port, desk port, checksum, length. So you're just handing a payload off to hardware, and you've already told it what your QP number is, and it already knows the destination port. It's just mechanical in how you slice it up and keep updating the links in the IP header and the UDP header.
Yeah, still, I mean, the fact
Right.
that if you
So that's where I'm kind of pushing back on the stack, because there's not really a whole lot of logic that's needed to make UDP packets, right?
fair, but
And this is defending like the legacy style
Yeah,
of,
yeah.
right,
But
not software-based protocols.
there is some contribution because you're doing all the parsing, etc. In the hardware. Could be a microsecond or less, but still, like it's not. If you're to put that stack, if you're to put that parsing of Ethernet, etc. in software, you'll get different performance numbers.
Well, hardware is going to parse the packet, right? So it knows which QP, for example, that a particular flow is going to. So it can tell you the demarcations of where's your L3 header, where's your L4 header, where's your RoCE header starting, if you wanted to do some things.
And the
in software.
QP header QP ID is in the UDP?
It's in the base transport header right after UDP.
After UDP, okay.
Yeah.
Yeah, okay.
Right. So again, the concept of an Ethernet header with no VLAN, 14 bytes, pretty static on where you can find things and parsing. And Tom's not here, so the whole concept of hardware parsing packets.
No, but I think it's fair to say that we parse and steer in hardware, but the protocol, the state of the protocol is completely software. Right? That's the separation.
Yeah.
So how is this for TCP? That's not done in hardware for the RoC. The RoCE over TCP, that does not do TCP headers and parsing in hardware, right? So how much is done by the kernel TCP stack there?
So for that case, it's entirely software-driven protocol.
Yes, okay. So
Yeah. So the TCP headers are created by the TCP stack.
okay, and your internal driver is basically creating FKBs and passing them to the TCP stack.
Our driver is passing the packet down to the hardware, yes. Right, I mean, TCP has decided when to send a packet and how much data to put into that packet. And then we take that SKB and send it down to hardware, yeah.
Yeah, okay. I'm also asking a little bit because it seemed sort of similar to this layer 4 offload for XDP thing we were discussing at one point,
Okay.
where you can sort of have XDP in this case, have a data buffer, and then just hook into the TCP stack to know where to put it and so on. Is that accurate?
So we don't have the protocol in hardware at all, right? I mean, other than the concept of knowing where the L4 header is, and when you're doing slicing on a GSO, for example, you have to know which headers to update, of course, which fields inside the header to update. But there's no state in the hardware. Sujit's comment was that hardware does not know about the buffer offloads like that, right? So we queue up an SKB just like any other NIC would queue up an SKB.
Okay.
I have a slightly different question. In your last slide, you had a teaser of congestion control, future
Yes.
discussion. I presume that referred to the ECNs and CNPs. At those speeds that we're working with today in the AI clusters, is the congestion notification route even viable for the software to react to the congestion in the network and do something meaningful with it? Or should we look for something more that is currently, hidden in the hardware and make that software controllable?
Yeah, this may be, okay, so the question is so let's take first things first. So the CNP, or rather ECN triggering CNP's route is obviously the only thing that's working right now in all of the networks that David was talking about. The question you're asking is the CNP return path, which is the responder seeing the CNP, the ECN generating a CNP in software, and then the requester seeing the update and then updating its rate happening in a fast enough rate. No, we have some hardware acceleration for that, and I don't think the reaction time is the problem there, right? Because the issue is not the rate control. The rate control is at 50 microseconds or higher, which is just fine for software. But it's the fact that you want to respond as quickly as possible, and yeah, we have some support for that. I don't think it's, like if you had a polling thread, if you had enough CPU to burn and you had a polling thread, that wouldn't be an issue either, right? Creating and pulling out a cache line and writing another cache line or route to IO in under, let's say, 10 mics is not that problematic. And if you have a 10 microsecond network and a 10 microsecond response and you're operating at 50 microsecond rate change, you have enough budget. That in itself is not an issue.
So I had one quick question for you. So you had mentioned when you started reintroducing your Linux TCP with Q pairs that you expected that to scale past 400 gigabits, but then you never said how or why. Can you expand on it a little bit?
So some experiments that we did 2021, early 2022, was how fast can Linux TCP be pushed, right? And we did some tricks at the device level so that we didn't have to actually push 400, 500 gigabits of data over a PCI 3 link, which you can't do. But the key was that we did modify the software stacks. We wanted to see how fast we could push them. And the highest we could do was like 640 something gigabits per second. And it was playing some of the games that I had listed on that earlier slide, like the MTU sweep, how much data you're pushing down a given socket, send call. So essentially, we learned from that what each one of these layers brings into play. So if you go back to that talk at LPC, memory management became one of the huge problems. And you see that in the perf top for this existing one with ConnectX 7. The very first thing at the top is things that the driver is doing around an SKB, and then you see a whole bunch of page pull stuff. With QPs and memory regions, we're not playing games with page pulls. TCP is currently SKB based only, So yes, we do have to suck it up and take the hit for creating the SKB. But we're not having to do a lot of copies. Not having to do any copies. So that helps. When you look at some of the other things that show up in this, the SKB GRO side of things, you have to have hardware GRO. Your hardware is going to have to tell you things that came in an order, so you create one SKB with a whole bunch of payload on it. So again, you're relying on hardware and bypassing things like a generic backlog of packets that have to be processed and hitting route lookups or hitting socket lookups or hitting any of those kinds of things. We don't need to do a socket lookup because we know which socket this flow is for, because we set up the flow steering rule and we're running it through a queue pair specific to that socket, right? And so when you, from the past analysis that we've done and the experiments that we've done and seeing where the different overhead is, we've gotten a pretty good feel for how fast we can make this work. And maybe next year's talk will include some detailed numbers.
So just a quick comment about this slide. Shouldn't be the case anymore, especially with hardware GRO. So just a quick comment about this slide. It shouldn't be the case anymore with hardware GRO because you don't copy the header anymore. This specific MLX5E copy SKB header.
This is a 6.8 kernel.
Yeah, I got it.
Unmodified. Okay. Yeah. So you're saying I should have been using Topatree and the hardware GRO, because the hardware GRO toggle in eTool wasn't showing up.
Yeah, because it was enabled and then disabled, and then we re-enabled. I don't remember which version has it.
Okay.
I can check, but
okay.
Like
so yeah, the guy that was setting up the servers kept playing around with the different GRO and LRO options, and I was like, oh, you don't want LRO, we want the hardware GRO. And one time I got that flag to show up in eTool, but I had jumped through enough hoops and I couldn't remember how to get that one. So, okay. Thank you for explaining that. All right. I guess that means we're done. No more questions? All right. Thanks, Leon, for showing up. The RDMA expert showing up at the networking conference, Netdev conference. I do appreciate your time.
You're welcome. Thank you for inviting me.